Okay, so topic 6.2, nuclear energy. Okay, so in topic 6.2, nuclear energy, the first thing that we need to learn is about nuclear reaction. So what does it mean by nuclear reaction? Okay, so what does it mean by nuclear reaction? Okay, so and before that is we learn what is nuclear energy lah. So what is nuclear energy? Nuclear energy is known as atomic energy released during nuclear reaction, such as radioactive decay, nuclear fission, and nuclear fusion. Okay, so nuclear energy is known as atomic energy. Why do we call it atomic energy also? Because this nuclear energy is contained within the nucleus of the atom, right? Okay, atom. Okay, so this is the nucleus. So inside the nucleus of the atom, there are energy stored inside. Why is it that got energy stored inside? It's very logical. Okay, if you just think, inside the nucleus, there are proton, right? Proton and proton are positive charge. So they should repel each other, right? The protons should repel each other. But why is it that the proton can stick together so close together in the nucleus? I thought that they are supposed to repel each other, right? Positive and positive. So why is it that they can stick together in the nucleus? Because there are energy that force them to stick together. Understand? There are energy that force them to stick together. So what happens is when the you can say like the like when the bond or like the thing that hold the energy that hold it together is broken, or when the proton is released, fly out, okay, when the proton fly out, break out from the nucleus, then that means the energy that is used to tie the proton in the nucleus is that part of the energy is no longer needed. Okay, you don't need that part of the energy anymore. So if you don't need that part of energy anymore, so that energy will be released. Okay, so because that energy is released from the nucleus, okay, come from the nucleus of the atom, so we call them nuclear energy. And because nucleus is inside the atom, so we also call it atomic energy also lah. So it's the energy that comes from the nucleus, energy that comes from the atom. Okay, so it says here that it is released during nuclear reaction. So nuclear reaction is like radioactive decay, nuclear fission, and nuclear fusion. So these three are nuclear reaction. Okay, you can see if you look at the word nuclear reaction, you can see why is it called nuclear reaction. Because radioactive decay, nuclear fission, nuclear fusion, these are all reactions that happen in the nucleus of the atom. So it's very logical to call it nuclear reaction. Okay, so why is it that the atomic energy or the nuclear energy can be released during radioactive decay? If you still remember, for example, the alpha decay. What happened in alpha decay? two proton, two neutron are released. Right now, released out as the alpha particle. So if the two proton, two neutrons are released from the nucleus, that means the energy that force that proton to remain inside the nucleus is no longer needed. So when the two proton, two neutrons fly out, it carry together that energy lah. Okay, it carry together that energy and fly out with high velocity. Okay, so that energy is released as kinetic energy of the alpha particle. Get the idea? Okay, so the kinetic energy of the alpha particle is from the energy that tie the proton, neutron together inside the nucleus. So when it is when it released, so that energy is no longer needed to tie the proton and neutron in the nucleus. So it is out and that energy become the kinetic energy of the alpha particle. Okay, get the idea? Yeah. So that is why the radioactive decay also when the nuclear energy is released. Okay, beta particle, beta decay also said when the neutron break down to become one proton, one electron, the electron is ejected in a very, very high velocity out from the nucleus. So then kinetic energy of the electron of the beta particle is from the nucleus, So it is nuclear energy. Okay, and then gamma decay. The gamma ray that come out from the nucleus carry energy right now. Okay, electromagnetic wave. It is a medium to transport energy. So the gamma ray transport energy from the nucleus. So that energy is nuclear energy. Okay. So now we want to look at nuclear fission and nuclear fusion. Okay, nuclear fission and nuclear fusion. So what is nuclear fission? Wrong study here. Nuclear. Okay. Nuclear. Okay. Change to L. Okay, nuclear fission is a nuclear reaction when a heavy nucleus split into two or more lighter nuclei while releasing a large amount of energy. So one unstable nucleus split into two or more lighter nuclei. Okay, so as you can see here, you have one uranium-235 nucleus. And what happened? In order to make it split, we need to make it become very, very unstable. This uranium-235 is already very unstable. But if we want the uranium-235 to undergo fission, that means we want the uranium-235 to split right now. Okay? Then we shoot one neutron into the uranium-235. So when the neutron is absorbed by the uranium-235, then this uranium-235 will become uranium-236. So this uranium-236 is extremely unstable. Okay, it's extremely unstable. Okay, this uranium-235 is already unstable. So when you absorb the neutron, it becomes even more unstable. Okay, even more unstable. It becomes more unstable or very, very unstable lah. So when it becomes very, very unstable, we will want to become stable in the shortest time possible. And the fastest way to become stable is by reducing the mass. And the fastest way to reduce the mass is to divide by half. So the uranium-236 split into two. Okay? Split into two. Become krypton 92 and barium 141. Okay? Become krypton 92 and barium 141. And at the same time, it also emits 3 neutrons. Okay? 3 neutrons. So this whole process, this whole thing is the process of nuclear fission. Okay? Nuclear fission. Okay, so of course, this nuclear fission not only can happen to uranium-235, it can also happen to other kind of unstable nucleus. But why is it that we use uranium-235 here? Because uranium-235 is a very big nucleus. Okay, you see the nuclear number is 235, so that means the number of proton and neutron end together is 235. So very, very big, very, very heavy nucleus. So this nucleus that is very heavy, have a very big mass, is very unstable. If it's very unstable, so that means it will be easier for it to split into two. Right now, the bigger the object, the easier it is to break it into two. Okay, to split. So because it's already very unstable, so when you shoot one neutron into the uranium-235, so you can make the uranium-235 to change into uranium-236 and immediately split into two. So that means you can control that. You can control when is it that you want the uranium-235 to split, to fission. You want it to fission right now, you shoot the neutron right now, and then it will fission right now. You want it to fission later, you don't shoot the neutron. You don't shoot the neutron, then the uranium-235 will not fission immediately. Okay, but that does not mean it will never split into two. It will not split into two. Okay, that does not mean that it will never split into two. The uranium-235 naturally, even naturally, if you don't purposely shoot a neutron into it, the uranium-235 can actually naturally split into two, can naturally undergo nuclear fission. But of course, this process is uncontrolled. That means you don't know when is it that is going to fission. You don't know which one. That means it's random and spontaneous. Okay, the process is random and spontaneous. You don't know when is it that is going to split. Okay, you don't know which one. You don't know when is it that is going to split. So you cannot wait lah, because if you want the nuclear energy right now, then you must be able to control when is it that it will split and release that energy. So the way that you control is to make it very, very unstable so that it can split immediately. And the way to do that is to shoot one neutron into the uranium-235. Okay, get the idea. So you see here, let's talk about the energy here. So this energy is in the form of one energy. It says energy release. So the energy release is one energy. Heat energy, kinetic energy, electrical energy, what kind of energy? So the answer here is kinetic energy. So you imagine that this krypton and barium is at first joined together. All the protons are joined together as uranium-236. So that means there are energy that tie the proton together in the nucleus. So when it's split, the energy will be converted into kinetic energy of the krypton and barium. Why is it that it will convert into kinetic energy. Because imagine this krypton is the nucleus is positively charged, right? A lot of proton. And then this barium also positively charged. The nucleus is positively charged because nucleus only have proton only, which is proton and neutron. Neutron have no charge. Proton is positive charge. So that means the nucleus is strongly positive charge. Strongly positive charge. So these two, they are strongly positive charge. Of course, they will repel each other, and they will move. They will fly in opposite direction when it split. I repeat, when the uranium-236 split, this krypton and barium, they will fly in opposite direction with very, very high velocity. Okay, kinetic energy. So when it flies in two opposite directions, very, very quickly, it will collide with other particles around it. Maybe got other uranium-235, maybe got other krypton, got other barium. So they will collide with other atoms, right now. Okay, this nucleus that fly in opposite direction, they will collide with other particles. So when it collide with other particles, it will make the other particle have kinetic energy also. That means the kinetic energy will spread. Okay, the kinetic energy of the krypton and barium will spread to other particles around it. And the other particle, when get more kinetic energy, it will also move and collide with more other particles, and the kinetic energy will be able to spread throughout the substance, throughout the object. So that means when the kinetic energy of the particle in the object increase, then that means the temperature will increase. So, okay, kinetic energy of particle increase, temperature increase. So that means the kinetic energy will convert into heat energy. So the whole substance or the whole object will become hot, or the temperature will increase. Okay, get the idea? Okay, can understand? So how is it? This is how we can get heat energy from nuclear fission. All right. Okay, this is nuclear fission. Okay, so let's look at the nuclear equation. The nuclear equation. This is called the nuclear equation because this shows the reaction that happened in the nucleus. That is why it's called the nuclear equation. Okay, so you see here uranium-235 plus 1 neutron, it becomes uranium-236. This uranium-236 only exists for a very, 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 very short time. Because this uranium-236 will immediately split into barium 141 and proton 92, and 3 neutron released from the nuclear fission. Okay, you can split, barium fly out, proton fly out, 3 neutrons fly out, and energy lah. So this energy means the energy inside the kinetic energy, the kinetic energy of the barium, of the proton, of the neutron. Okay, the kinetic. So all of this energy, it will spread out in the substance and cause the temperature to increase. Okay, so we get heat energy. So this is nuclear fission. Next, we want to look at nuclear fusion. Okay, nuclear fusion is a nuclear reaction in which small and light nuclei fuse to form a heavier nucleus while releasing a large amount of energy. This nuclear reaction happens under extremely high temperature and pressure. Okay, so nuclear fusion is the opposite of nuclear fission. Nuclear fission, one very heavy, very big mass, unstable nucleus, split into two smaller and lighter nucleus. Okay, on right. In nuclear fusion, is the opposite. Small and light nuclei fuse, that means join together and become a heavier nucleus, that means nucleus with higher mass. While at the same time, it will also release a large amount of energy. Okay, so why is it that this nuclear reaction need to happen under extremely high temperature and high pressure? Because in order for the two small and light nucleus to fuse together, these two small and light nucleus, it will need to move very fast and they will need to collide together. That means two small nucleus, they move and coincidentally they will knock into each other and then join together, become one. Okay? Become one. So that is why it needs extremely high temperature so that the small and light nuclei have enough kinetic energy and can move very, very fast. When it moves very, very fast, then only it can collide with each other and join together. If the kinetic energy is not enough, then it will collide and it will just bounce off. Okay, if kinetic energy not enough, it will collide and then just bounce off in opposite direction. Okay, get the idea. And also need very high pressure because the high pressure will help it to fuse together. Right. Move very fast, collide together, and outside got very high pressure, push it together. So this makes the two small nucleus join together, fuse together, and become one heavier nucleus. Okay, so let's look at the example for the nuclear fusion. Nuclear fusion between deuterium and tritium occur to form a heavier helium nucleus. Energy and one neutron is released. Okay, so again, you see this deuterium and tritium, they are both hydrogen isotope. This is hydrogen 2, deuterium hydrogen 2. This tritium is hydrogen 3. So these two hydrogen isotopes, they are very small. Okay, only one proton. This one proton, 2 neutron. This one proton, 1 neutron. They join together, fuse together, and then become helium nucleus. Okay, and then you see there is one extra neutron. So the extra neutron will fly out. Okay, so when it becomes helium nucleus and neutron, so this helium nucleus and neutron again, they have a lot of energy. What energy? Kinetic energy. So it will move very quickly. Okay, this helium nucleus, this neutron, it will be able to move with a high velocity. So again, it will be able to collide with other particles in the surrounding, spread the kinetic energy. So the total energy of the particle will increase, so the temperature will increase. So this is how to get heat energy from nuclear fusion. Okay? Alright. So let's look at the nuclear equation. So this is deuterium plus tritium to get helium nucleus. Okay? And 1 neutron plus energy. Okay? So this is nuclear fusion. So for your information, I hope that you still remember that you got learned before that nuclear fusion is how the sun, our sun, the star, get the energy. Okay, how is it that our sun can release so much energy? So all of this energy are produced with nuclear fusion. Okay, so the nuclear fusion happens at the core of the sun. Okay, next. The relationship between energy released during nuclear reaction and mass effect. Okay, relationship between energy released during nuclear reaction and mass effect. Okay, so first we need to do a little bit of revision. I'm sure that this atomic mass unit you already got learned in chemistry. Okay, so what is atomic mass unit? Atomic mass unit, or in short form is AMU, is a measurement of the mass of an atom. Units such as gram or kilogram are not suitable because the mass of an atom is too small. So it is based on relative comparison between the mass of an atom with the mass of one carbon-12 atom. Okay, get the idea. So we use the mass of carbon atom as a unit of measurement. Okay, as a unit, as a standard like a ruler like that. We use the mass of carbon-12 atom as a ruler, as a comparison to compare the mass of different atoms. Okay, so carbon-12 is used as a reference because carbon can be found in many components on Earth. Okay, because carbon is very commonly found, okay, it's all over the Earth. So use carbon-12 atom as the unit of reference. Okay, so the Avogadro number, okay, this Avogadro number also you got learned chemistry. Okay, the Avogadro number is the number of atoms found in 1 mole of carbon-12. So the number of 1 mole is wait, okay, so the Avogadro number is 6.02 times 10 power by 23. Okay, 6.02 times 10 power by 23. So that means 1 mole of carbon-12, 1 mole of carbon-12 is 6.02 times 10 power by 23 atom. Okay? So, or in another way to say is, if you have 6.02 times 10 power by 23 atom of carbon, then you say you have 1 mole of carbon. Okay, 1 mole of carbon. So 1 mole of anything is to have this amount of that object. Okay, if you say you have 1 mole of 1 mole of apple, so that means you have 6.02 times 10 power by 23 apple. Okay. Okay, so mass of 1 carbon-12 atom is 12 atomic units. So we take it that the mass of carbon-12 is 12 atomic mass unit. So we use this mass of carbon as a measurement. Okay, so that means 1 atomic mass unit is defined as a mass equals to 1/12 that of the mass of a carbon-12 atom. So this is the mass of 1 atomic mass unit. So mass of 1 mole of carbon-12 equals to wait, Avogadro number is okay, so the mass of 1 mole of carbon-12 is is 0.01. plus okay, yeah. Okay, yeah, 12 gram. So that means mass of 1 mole of carbon 12 is actually 0.012 kilogram. Okay, a little bit open this up. Okay, yeah. So 1 mole of carbon 12 is 12 gram. Okay, 1 mole mass of 1 mole of carbon 12 is 12 grams, so it's 0.012 kilogram. So the mass of one carbon 12 atom is you take 0.012. Okay, 0.012 kilogram divided by 1 mole of atom. So how many atoms? 6.02. 6.02 times 10 power by 53. So yeah. Okay, so it will be about 1.99 times 10 power by 56 kilogram. Okay, so this is the mass of one carbon 12 atom. Okay, so if this is the mass of one carbon 12 atom, so that means one atomic mass unit is equal to how many kilogram? So it will be equal to 1 over 12 times the 0.012 over 6.02 times 10 power by 23. That means it would be 1/12 of this of 1 carbon 12 atom. Okay. Okay, so one atomic mass unit would be 1.66 times 10 power by negative 27 kilogram. Okay, so this is the mass of one atomic mass unit. Okay. All right. Okay, so this is actually just division. Actually, all of these you should learn. Okay, now we want to go into what is mass effect. Okay, just now we say that. Okay, just now we say that okay, relationship between energy released during nuclear reaction and mass effect. Okay, so we want to look at what is mass effect. Okay, in a nuclear reaction or radioactive decay, the total mass of the decay product is always less than the mass of the radioactive nucleus. So this loss of mass is known as mass effect. Okay? So don't care whether it is during radioactive decay, is it nuclear fission or nuclear fusion, the total mass of the product is always less than the mass of the original substances. Okay, all the mass of the original substance is more than all the mass of the product. So for example here, so the mass of the neutron is 1.00867 atomic mass unit. The mass of the uranium-235 is 235.04392 atomic mass unit. After join together, it will split, okay, become krypton 91.92611 atomic mass unit, and then 3 times 1.00867 atomic mass unit because of 3 neutron. And then barium 140.9141. Okay, so we see here total mass before fission. This plus this get 236.05259 atomic mass unit. And then total mass after fission is plus this plus this. All these three add together, you get 235.86653, which is less than this one. You see or not? This is 236, this is 235. So sum of the mass is lost. Don't know gone where already. And then the total amount of mass that is lost is 0.18606. Okay, just by taking the total mass before fission, we minus total mass after fission, so we get this number. Okay, so this amount of mass that is lost, we call it mass effect. Okay, get the idea. So the total mass that is lost, we call mass defect. All right. So what we found is actually, if I'm not mistaken, is Albert Einstein. Okay, Albert Einstein, after doing many experiments, he found that energy release during nuclear reaction is directly proportional to the mass effect. So Albert Einstein, after do experiment, he found that, okay, he draw a graph. He found that, okay, so this is the mass effect. This is the energy release. And he found that it is directly proportional. So that means he come to a conclusion that the energy release actually is from the mass defect. That means this mass that is lost is the mass that convert into energy. Or another word is energy have mass. Okay, so this energy at first is stored in the nucleus, right? So when the energy release, the total mass become less. So this tells us that energy actually have mass. Okay, so any object that have more energy actually have greater mass. Understand? Any object that have greater energy actually have greater mass. Okay, so that means, for example, okay, let's say you have water. This water at first is 30 degrees Celsius. When you heat the water until become 100 degrees Celsius, actually the mass of the water at 100 degrees Celsius is more than the mass of the water at 30 degrees Celsius. Get the idea? Okay? Another example is when you are sitting in the car. Okay, you sit in the car. When the car is not moving 0 meters per second, your mass is lower. When the mass and when the velocity of the car is 10 meters per second, your velocity also increase, right? You didn't do anything. You just sit there only. The car move and push you and increase your velocity. So that means the kinetic energy of your body increase, right? Kinetic energy increase. So when the kinetic energy of your body increase, then the mass of your body also increase. So actually, your body, when you're moving, have greater mass compared to when you are not moving. Okay? So energy actually have mass. Okay? Understand? So so Albert Einstein, from this graph, he found out that the gradient of the graph, okay, the gradient of the graph is equal to speed of light squared. Okay, equal to the square of the speed of light. Okay, this gradient is equal to the square of the speed of light. So when he construct the linear equation of this graph, y equal mx plus c, this y is the energy release, this c is 0 because pass through 0, x is the mass effect. Okay, so this gradient is c squared. Okay, so we get the equation of E equals mc squared. So very famous equation lah, E equal mc squared. So this is how we get the equation of E equal mc squared. Where during nuclear reaction, okay, during nuclear reaction includes radioactive decay. That means the alpha decay, beta decay, gamma decay. Okay, include the alpha, beta, gamma decay. All include in nuclear. All is radioactive decay, and radioactive decay is included in nuclear reaction. Okay, so during nuclear reaction, that means during radioactive decay, during nuclear fission, during nuclear fusion, energy release and the total mass decrease. Okay, so basically this mass is the mass of the energy. So when the energy release, the mass decrease. So that is why we have mass effect. Okay, okay. So nuclear energy can also be expressed in the unit of mega electron volt. Okay, mega electron volt is the amount of energy that is contained in the charge of one electron. Okay, how much energy that is contained within the charge of one electron. Why is it that we want to use this unit of mega electron volt? Is when we want to produce electrical energy by using nuclear energy. Okay, we have nuclear power station right now. So the nuclear power station use the nuclear reaction to produce electrical energy. So how many mega electron volt can be produced from the nuclear energy? Okay, so that's why we use the unit of mega electron volt lah. But usually we don't use that. If in other situation, we use the unit of joule as a unit for energy. Okay, we use the unit of joule for unit of energy. All right. So next, we want to look at examples. Okay, solving problems involving nuclear energy due to radioactive decay and nuclear reaction. Okay, so let's look at the example. The equation below show radium 226 decay in radon 222 by emitting alpha particle. Okay, so this is the alpha particle, the helium nucleus. Given that the mass of radium 226 is 226.54 atomic mass unit, radon is 222.018 atomic mass unit, and the helium nucleus is 4.003 atomic mass unit. Calculate the nuclear energy released. Okay, so the equation to calculate nuclear energy release is E equals mc squared. So that means if we want to calculate how much energy, we need the mass effect. Okay, we need to calculate how much mass is lost. So first we calculate the mass effect first. So the mass effect will be all of this mass minus all of this mass. Okay, this mass minus this mass. Okay, so the radium 226.54 minus 222.018 plus 4.003. Okay, so get so the mass effect is 0.519 atomic mass unit. Okay, this is in atomic mass unit. But if you want to put the mass effect into the E equal mc squared, this atomic mass unit must be converted into kilogram. So this will be equal to 0.519 atomic mass unit. So one atomic mass unit is equal to 1.66 times 10 power negative 57. So 0.519 atomic mass unit times 1.66 times 10 power by negative 27. Then get you get 8.6154 times 10 power by negative 28 kilogram. So this is the mass effect. So we put this into E equal mc squared. So the mass effect is 8.6154 times 10 power by negative 28 times the square of speed of light, 3 times 10 power by 8 squared. So we will get okay, we will get 7.75386 times 10 power by negative 11 joule of energy. Okay, so 7.75386 and round off to become 7.75 lah. Or you can minimum 2 decimal place, so 7.75 or 7.7589. Okay, but of course I will recommend that you write all of them because it's not that long, right? Okay, so in physics, we always emphasize on accuracy. So the greater the accuracy, the better. So we don't simply round off the number. Okay, try to avoid rounding off number as much as possible. Okay, not one higher accuracy. So, okay, let's look at another example. Example 2. Okay, the sun is the source of energy to the earth, and this energy is produced by the nuclear fusion in the form of the sun, shown in the following equation. So calculate the nuclear energy released in joule. Alright, so again, if you want to calculate the nuclear energy release, so we use E equal mc squared. So we need the mass effect. So we take all of this mass minus all of this mass. Okay, this mass minus this mass, then we get the mass effect. So the mass effect is, okay, deuterium. Deuterium is 2.014. Okay, and then plus tritium 3.016. Okay, this whole thing minus hidden nucleus 4.003 plus 1 neutron 1.009. Okay, so get 'okay, the mass effect is 0.018 atomic mass unit. So again, we need to convert this into kilogram. So 0.018 times 1.66 times 10 power negative 27. So we get 2.988 times 10 power by negative 29 kilogram. So this is the mass effect. Put the mass effect into E equal mc squared. 2.988 times 10 power by negative 9 times 10 power 8 squared. So get 2.6892 times 10 power by negative 12 joule. Okay? Alright, so this is the amount of energy that released from the fusion of one deuterium and one tritium. Okay? The amount of energy looks like very small, but remember, the sun is very, very big, so there are billions and trillions of deuterium and tritium that fuse together at the same time. So it will be able to release an extremely large amount of energy. Okay, so same with this also. The amount of energy looks like very small. Okay, 10 times 10 power by negative 11 joule. So looks like very small, but remember, atoms are very, very small. So in one small dot, you have billions of atoms here. Billions of atoms in just one dot or one grain of dust. Okay, a small dust already have billions of atoms. So when trillions of unstable nucleus. They undergo radioactive decay, undergo nuclear fusion at the same time. So the combined amount of energy that is extremely large. Okay, we have a lot. So in ratio, if we compare, the energy that is released from nuclear reaction is much higher compared with other kind of method like burning wood, burning coal, burning natural gas, burning petrol. Okay, mass to mass up, compare mass 1 kilogram of uranium after undergo fission, the amount of energy is many times more than burning 1 kilogram of wood or 1 kilogram of coal or burning 1 kilogram of natural gas, 1 kilogram of petrol, and so on. Okay. So that's why we say that nuclear energy will get a lot of energy from nuclear reaction. Okay. All right. So next, we want to look at generation of electrical energy in the nuclear reactor. So the basic concept you already got learned in the lower form science also, form 3 if I'm not mistaken. So basically, how do we get electrical energy in nuclear power plant is, you see, this is the nuclear reactor. Okay, this is a nuclear reactor. So that means inside this nuclear reactor, heat energy is produced from nuclear reaction. Okay, from nuclear fission, heat energy is produced. So this water pump the water into the nuclear reactor. The water will be heated up. The water becomes very hot. Of course, this water is not normal water lah. Okay, it's heavy water if I'm not mistaken. Okay, so this water has much higher specific capacity than normal water, and under very high pressure, the water temperature can reach very high. Okay, without boiling. That means the boiling point can be very high. I'm sure that you already know that under high pressure, the pressure can affect the boiling point. The greater the pressure, the greater the boiling point. Okay, so the opposite also true lah. That means if lower pressure, then the boiling point will be lower also. So that means if you go to a very high mountain, for example, Mount Everest, the boiling point of water on top of Mount Everest is lower compared to the boiling point here at sea level. So, for example, here at sea level, the boiling point is 100 degrees Celsius. But on top of the mountain, the boiling point is lower than that. I can't remember how much, I think 80 something or 90 something degrees Celsius. Okay, the boiling point is lower than 100 degrees Celsius. Okay. So that means if you go to space or in vacuum, the boiling point of water will be much lower. Okay, even though very easy the water can turn gas in vacuum. Okay. All right. So let's continue. Okay, so here produce heat energy. Heat the water. The water that go into the nuclear reactor will be used to heat up other water. Okay, you see here got another water pump. So you see this water that go into a nuclear reactor, it just flow inside this pipe. Okay, it just flow inside this pipe. Okay, it doesn't go out. The reason is this is for safety reason to reduce the risk of the leakage of radioactive substance, because there are chances that actually this water that goes into the reactor definitely will be contaminated with radioactive substance. That means the unstable this water will have stable nucleus. Okay, so that means the water becomes radioactive. When the unstable nucleus decay, it will release radiation. Okay, so that's why we don't want this water to come out. Instead, we use this water that goes to the reactor to heat up another water. So this water, you see, is separated. So this water that is pumped by the water pump going in here is heated by the water from the reactor, and then the water will turn to steam. Under high pressure, the steam will flow with very high velocity. That means like a lot of kinetic energy. So this high kinetic energy steam will act like a very strong wind, like that, like a very strong wind to blow on the turbine, to push the turbine will rotate. And then the rotating turbine will rotate the generator will convert the kinetic energy into electrical energy. Okay? So this hot water that turns to steam, after the steam rotates the turbine, the steam will lose the kinetic energy, and then it will go to the condenser. So in the condenser here, the condenser will cool down the steam so that the steam will turn back into water. Okay, that's why it's called condenser lah. So that the steam can undergo condensation. So the steam undergo condensation, turn back into water, and then so that it can be pumped back into this water tank, heated by the water from the reactor, turn to steam, and continue to rotate the turbine. Okay, so in order to cool down the steam, other water is pumped into the condenser to cool down the steam. So you see, water pumped in, usually this water is from sea, from the sea or from river, usually from the sea. So that is why the nuclear power plant are usually built near the sea. Okay? Built near the sea. So the water is pumped in to cool down the water. And then the water from the sea pumped in after cool down. Then cool down, that means the water will absorb the heat energy from the steam. So the water becomes hot. The hot water will flow out and into the cooling tower. So the cooling tower, you have a cooling pin. It will absorb the heat energy and turn to steam. Okay, release the heat energy. So that is why you see that there are white color smoke that come out from the cooling tower. So actually, this white color smoke is steam. Because this water is very hot, after pass through the condenser, it becomes very hot, it will boil and turn to steam. So a lot of water that turn to steam. Okay, of course there are water that does not turn to steam, it will just release out. Okay, so this is the general structure of the nuclear power plant. This is already this is just revision of what you already learned in Form 3. Okay, so what is it that we want to concentrate on here is how do the nuclear reactor works. Okay, how the nuclear reactor works. How to the nuclear reactor work. But of course, before that, we need to learn something about the chain reaction. Okay, so in the nuclear reactor, the fission of uranium-235 nucleus produce two daughter nuclei. That means the barium and the krypton. Okay, but actually not necessarily barium and krypton. It can actually, when it's split, not necessarily it will split into barium and krypton. It can split into other kind of element that have roughly the same mass. Okay, understand? Not necessarily barium and krypton. This is just example. Okay, when the uranium-235 becomes uranium-236 and split, it can split into other kind of element also, not necessarily barium and plutonium. Okay, so please do not get confused when, for example, pressing come out and it says that the uranium is other kind of element, not barium and plutonium. Okay. Okay, so when the uranium-235 split to copper nuclide, with 3 fast-moving neutron released. Okay, 3 fast-moving neutron release and also release a large amount of energy. Again, this large amount of energy is in the form of kinetic energy of the daughter nuclide and the fast-moving neutron. Fast-moving neutron. Okay, so this neutron will bombard other uranium nuclide and release more neutrons through continuous nuclear fission. So this continuous reaction is known as chain reaction. Okay, so what does it mean here is one neutron go into one uranium-235. So this uranium-235 will turn into uranium-236 plus and then split out. Okay, but we skip out. We don't talk about the uranium-236 because the uranium-236 only exists for a very, very short amount of time. It absorbs 235, absorb one neutron, become 236 and then immediately the 236 will split into 2 daughter nuclei. In this case, it's krypton and barium. Okay? So when it split, when it undergoes fission into krypton and barium, at the same time also 3 neutrons is released. So these 3 fast-moving neutrons will, if it is successful to go into other uranium-235. Remember, okay, you see it's like, okay, you have one lump of substance. So in this substance, you have uranium-235. So there are many atoms, many atoms of uranium-235. So that means if one of them split and release 3 neutrons, so this neutron maybe can go into this uranium-235, this one goes to this uranium-235, this one goes to this uranium-235. So it will make this uranium-235 to split and release 3 more neutrons. 1 neutron, 2 neutrons, 3 neutrons. So these 3 neutrons that come out, if it is successful in going into other uranium-235, I repeat that if it is successful, it's not necessarily be able to go into another uranium-235. Sometimes it is not successful, it just pass through and escape. For example, sometimes it is not successful to go or just split right out. Okay, just right out. Didn't meet with other uranium-235. So in order to increase the chances of the neutron to go into uranium-235, so this material, or we say the nuclear fuel, okay, this uranium-235 that we want to use to generate a lot of heat energy, we need to make sure that the concentration of the uranium-235 must be high enough. Okay, the concentration must be high enough. If the concentration or the number of uranium-235 is not very high, then that means the neutron that fly out may not go into other uranium-235. If it didn't go into uranium-235, then it cannot continue to generate energy. So this is called the chain reaction because one uranium-235 fission, it can continue to make other uranium-235 to undergo fission. Fission, release neutron, go into U-235, fission again, release neutron, this neutron goes to other uranium-235 and continue to fission and produce more and more neutron and more energy. Okay, more and more uranium-235 to fission and produce more and more energy. Okay, so this is what we call the chain reaction. We start it and then it will continue and continue. Same like when you burn the paper right now, actually when you burn paper, it is a chain reaction also. Right now. Why is it that you just burn the paper on one side and then you don't need to continue to burn? It will burn by itself. The fire will spread. Because when you burn the paper on one side, okay, you have a strip of paper, you burn one side, and then chemical reaction will happen right now. So the chemical reaction release heat energy. So this heat energy that is released from the burning of the paper on this side, it will cause the next molecule to combust, to burn. So the burning will release energy, and the energy will make the next one burn, and the next one to burn, and the next one to burn, to burn. So it's the same lah, okay, but chain reaction like that. Understand? So this in this case, this is nuclear reaction lah, where the neutron fly out because it produces more neutron, the neutron goes to other uranium, and the other uranium will split and produce more neutron like that lah. Okay? Get the idea. Okay. So sorry, some wait a minute. Sorry. Okay, continue. Okay, continue. Sorry about that. Continue. Okay, so let's look at how the nuclear reactor works. Okay, let's look at how the nuclear reactor works. Okay, so what is important is inside here. Okay, most important is inside here. Okay, you see it says here, this, okay, Okay, so this one, the white color one, this is labeled as the uranium rod. So the uranium rod used as fuel for producing nuclear energy through nuclear fission reaction. So that means inside here, inside this white color one, you have a lot of you have a lot of uranium. Okay, you have a lot of uranium inside here. So the uranium inside here will undergo fission when one neutron is absorbed and then it will undergo fission. Understand? Okay. So how is it that you start the fission? Actually, you have many uranium rods, but where do the first neutron come from? The first neutron come from what they do is they insert a substance that can release neutron. Okay, there are unstable nucleus that when they decay, they will release neutron. Okay, so what they do is they take that substance, put into a rod also, and then insert into the center. When insert into the center, and then that substance will release a lot of neutron. Neutron will come out. So that neutron that come out will start the fission, will start the nuclear fission chain reaction. So when the chain reaction started already, and then they can take out the starter, okay, that first rod that is the neutron they can take out, and then just let the chain reaction continue to happen lah. Okay, so next we want to look at this one. You see this one, the gray color one is the moderator. So this moderator slow down the fast-moving neutron release so that nuclear fission can occur, made from materials such as graphite or water. Okay, so you see, why does it say that we need a moderator to slow down the fast-moving neutron so that nuclear fission can occur? What does this mean? Because you see, this neutron that fly out, it has a lot of energy. That means it is moving with very high velocity. The velocity is actually too high. That means it's moving too fast, understand? If it's moving too fast, it will be very difficult to be absorbed by uranium-235. That means what happened is it will just pass through the uranium-235. Understand? Okay? If it's too fast, it will just penetrate through. It will not be absorbed by the uranium-235. Remember, the neutron must go inside, absorbed by the uranium-235, so the uranium-235 becomes uranium-236, and then it will become very unstable and it will split. So in order to make the neutron travel at a suitable speed, it needs to be slowed down. So to slow down the neutron, use a moderator. So this moderator is made from materials such as graphite or water. So this graphite, actually the new version of the reactor is, I think, it's mostly water, really water. So meaning, when the neutron that come out pass through the graphite or the water, the neutron will slow down, and then when it go into the neighboring uranium rod, then it will be able to be absorbed by the uranium in the neighboring uranium rod. Okay, meaning like this, means like this. Okay, so let's say here got one uranium that undergo fission. So got 1, 2, 3 neutron fly out. So this neutron fly out, pass through the moderator, and just fly out because there is no other uranium rod here. But this one that fly out, after pass through the moderator, the speed will be slowed down to a suitable speed. So that means when this neutron go into the uranium rod here, so it will be able to be absorbed by the uranium rod, absorbed by the uranium in this uranium rod. So the uranium inside here can undergo fission. This one I'll just write out, okay, doesn't go into any other uranium. Okay, but of course the actual nuclear reactor is not so small, it's not consist of two uranium rods. Okay, there are many uranium rods. Okay, some even have hundreds and hundreds of uranium rods. Okay, understand? Okay, wait. Okay, for example, this picture that you see. Okay, you see this is the nuclear reactor. So there are many holes. There are many holes. So each of these holes is where you can put the uranium rod. Okay, you can put the uranium rod. Okay, for example, this one. For example, this one, you can see that there are many holes there. So each of these holes you can insert the uranium rod. Okay, so this one it will be filled up with water. Okay, it will be filled up with water so that in between the uranium rod you have water that acts as the moderator. So that means when the neutron fly out, pass through the water, and then it will slow down until at the suitable speed okay, to reach the suitable speed to be absorbed by other. Okay, you get the idea? Yeah. Okay, so next is the control rod. Of course, we need something that can control the nuclear reaction right now, so that if we want more energy, we can increase the amount of nuclear reaction. If we want to decrease the amount of energy released, we can slow down the chain reaction. or if you want to turn off, we must be able to turn off the reactor lah. Okay, this is very important. Can turn on, turn off, can control. This is very important. Okay. So you see, in order to control, we use a control rod. So control rod can control the reaction rate by absorbing excess neutron. So it's made from boron or cadmium. Okay, it is made from boron or cadmium. So why made from boron or cadmium? Because this boron and cadmium, when the neutron go into the boron rod, then the neutron will be captured by the boron. So the neutron will not be able to escape. So when you insert the control rod, then the control rod will be able to absorb the neutron. All the neutron that go into, if the neutron go into the control rod, then the neutron will be captured by the boron inside the control rod. Then that means the number of neutrons inside the reactor will decrease. So slowly, the number of neutrons will decrease, and then the nuclear reaction will stop. Okay, the reason is because you see, it's very simple. Okay, so for example here, okay, out of 3 neutrons, if 3 neutrons go into the uranium, then the uranium can produce more neutrons, right? But if you insert boron rod, let's say out of the 3 neutrons, 2 neutrons absorbed by the boron, so only 1 neutron go into uranium. So this uranium split into 3 neutrons, and then let's say that this time these 2 also absorb, left 1 only, and this one, let's say, not successful in getting into other uranium. So then the chain reaction will stop. See, and increase or slow down the reaction or stop the reaction altogether. Okay, so that is the function of the control rod. So this control rod is like, for example, this one. Okay, this one, this are the control rod. So this control rod can be inserted and can be removed. So if you want to slow down the reaction, then you insert the control rod. You push the control rod, go in. Of course, you use machine, not push with they use machine to push in the control rod, and then the number of neutrons can increase. If they want to increase the amount of energy released, so they remove the control rod, they pull the control rod out, and then more neutron is free to go in other uranium. Okay, okay. So other kind of safety feature. Thick concrete wall. This wall is a thick concrete wall to prevent radioactive radiation from leaking to the surrounding. Water as cooling agent absorb heat energy from the chain reaction to generate steam. This can also control the temperature of the reactor. So this cooling system is very important. If you know about the famous nuclear accident, nuclear disaster, the Chernobyl, it started because of the failure of the cooling system. Because the cooling systems cannot function properly, so the temperature of the reactor become too high and cause a lot of other malfunction, a lot of other damage. Okay? Yeah. Okay, so let's continue a bit more. Again, finish up this topic. Okay, so the use of nuclear energy as an alternative source to generate electrical energy. So the advantage of using nuclear power to generate electricity, okay, the cost to operate a power plant is cheaper. The usage of fossil fuel is reduced. No air pollution with no sulfur dioxide and carbon dioxide released into the atmosphere. Safer as very few accidents were reported if compared to fossil fuel power plant. A small amount of fuel is needed to produce high electrical energy. many job opportunities are provided for power plant operation. Okay, so these are the advantages of using nuclear power. And then, of course, there are disadvantages. So what are the disadvantages? With the high safety measurement, the cost to build a power plant is too expensive. Okay, it's very. If you want to build the power plant, it's very expensive. But after build, to run it in the long term, if you count the long term, then it's cheap. Okay, cheap in the long term, but you have to put in a lot of money when you want to build. Okay, number two, produce radioactive waste that is dangerous to the environment and residents. So also the cost of disposing of radioactive waste is expensive. You have to think of many ways to get rid of the radioactive waste. Okay, high risk of disaster. For example, if you build in an area that have natural disasters like earthquake and so on, then there's a risk. Okay, the risk of course is bigger for disaster. And of course, no matter how high and how advanced the technology is, if the human make mistake, if the human being that control the machine make mistake, also it can cause disaster to happen, like what happened in Chernobyl. Okay, it's a human error. Okay, so there is a risk. If nothing go wrong, then very nice. But if something go wrong, then the problem and the damage is very big. Okay, but for your information, don't worry that the nuclear power plant will explode like atomic bomb. Okay, it will not explode like atomic bomb. I tell you first, it will never explode like nuclear bomb or atomic bomb because the uranium that is used, okay, the uranium fuel that is used, actually the concentration is not very high. That means the number of uranium-235 is not very high. So that means the number of neutrons that can go into other uranium is actually not a lot. Out of the 3 neutrons, maybe 2 neutrons can go in. Sometimes maybe 1 neutron can find other uranium-235. This is different with an atomic bomb or nuclear bomb, where the concentration of uranium-235 is very high. That means all of the neutrons can easily find other uranium-235 to go in. Okay, and also the way that it is constructed, the working structure, the working principle of a bomb compared to the nuclear reactor is totally different. So that means in a nuclear reactor, the energy is slowly released for a very long time. Slowly release energy. But in atomic bomb, almost all of the uranium split at the same time. That is how is it that you can get a very powerful explosion. A big release of energy in a very short time. Then you get an explosion. Okay, so some people that don't understand, they thought that nuclear power plant very dangerous because if something go wrong, then the nuclear power plant will explode like bomb or that more. Okay, it will never explode like bomb. Okay, so please do not have this conception. Okay, so anyway, although there are a lot of disadvantages, but the advantage actually outweighs the disadvantage. Okay, as long as it is taken care of properly, nuclear energy is one of the future. Okay, it's the future for us to reduce climate change, reduce greenhouse gases, and so on. All right, so finish the chapter 6. Okay, finish the chapter 6. Okay.